Hello and welcome to the logic of it all. In this video, we are going to start talking about logical arguments. Now, what is a logical argument? A logical argument is the kind of approach that a scientist or even a detective follows, where you have a set of statements that you either know to be true or assume to be true, like axioms in mathematics and so on. And then you want to see what new statements you can deduce from your assumptions and the things that you know to be true. What can we show that follows from what we already know? So this is called a logical argument. And to be able to talk about this more clearly, we introduce some terminology. So for example, in a logical argument, the assumptions or the statements that you assume to be true or know to be true, we call them the premises of your argument. And the things that you want to show that follow from your hypothesis or premises, we call them the conclusions of your logical arguments. So premises, hypothesis versus conclusions. And here we are going to look at two types of logical arguments. The first type, which we will investigate in this video, is based on the truth table of your premises and your conclusion, which is also called the semantics of your propositions. And then later on, we will look at a different way of validating a logical argument, showing that a logical argument is valid, that is not based on the truth table. Now, there are pros and cons to these two approaches, as we will see later, but just to give you a high-level idea, the first approach will, as we will see in this video, is going to be straightforward, and it doesn't require any kind of creativity. You just follow a procedure, and it always tells you whether a logical argument is valid or not. The problem with the first approach is, if your premises and your conclusion they have many variables involved, then the size of your truth table is going to grow exponentially. And that means that this approach is easy but not as efficient. The second approach is not as straightforward, so it requires a little bit of thinking and requires a little bit of creativity in some cases, but it could potentially be shorter and more efficient. As I said, in this video, we are going to focus only on the first approach, and then in later videos, we will talk about the approach that uses only the syntax. So, when can we say that the proposition is a semantic consequence of some premises? Okay. Again, if you think about it, we can say that something follows from a set of assumptions or hypotheses whenever all our premises are true, the conclusion is true as well. So that's basically the definition. We say that P is a semantic consequence of a set of premises if whenever all the premises are true, your conclusion is also true. Very simple. Now, the way that we write this is we list all our hypotheses or premises here on the left side. Now, for generality, I named them H1, hypothesis 1, hypothesis 2, up to hypothesis n. So these are the things that you either know or assume to be true. And then on the right side, you have what you want to show that follows your conclusion. Okay? And this is called double turnstile. So the way that you need to understand this is when we write something like this, what it means is C is a semantic consequence of the assumptions or hypothesis or premises H1, H2, up to Hn. Now, this could be a little bit abstract, so let's see how we actually do this in practice. There's a very simple algorithm, as I said, that applies to all examples when we talk about semantic consequences. And the algorithm is as follows. First, we create a truth table that has columns for all our premises as well as our consequence. Okay, and of course, all their subformulas, because we need the truth value of the subformulas to be able to know the truth value of our premises and also the consequence. So create that truth table, fill it out, as we discussed in previous videos. Then, again, if you remember from a couple of slides before, what we are interested in is whenever all the premises are true, the conclusion must be true as well. So it doesn't matter if your truth table has 8 rows or 16 rows or 32 rows or 64 and so on. In this scenario, when we are trying to confirm whether whether some formula is a semantic consequence of our set of premises, we are only interested in the rows where all our premises are true. Okay, so we only focus on those rows. And then there are two possibilities. It's either that on all those rows where your premises are true, on each and every one of them, your consequence or your conclusion is also true. In that case, we have shown that our argument is valid. On the other hand, if that's not the case, which means if there is even one or more rows where all your premises are true but the conclusion is not, then we say that this argument is not valid. Okay, so it's very simple and it applies to no matter how many premises you have and so on, the same algorithm works. But as you will see, if we have a lot of variables involved, it becomes inefficient because the table is going to grow exponentially. Now, here's our first example. So my what I want to show is that I want to show P and Q is a semantic consequence of these two propositions. If P then Q and P. So I have two premises, namely P, if P then Q and P, and my conclusion is P and Q. So what I need to do is, based on the algorithm that we had on the previous slide, I need to create a truth table for all my premises as well as my conclusion. Now, the first step, if you remember from our previous videos, is to decide how many rows I need. And if you look at these formulas, we have only two variables, P and Q, which means that there are 4 possible scenarios, which means my truth table needs 4 rows. So the top row is for the name of the formulas, but other than that, we need 4 more rows. And also, if you remember, we need columns for each variable. So a column for P, a column for Q, and then from P and Q, I can have the conjunction P and Q. I can also have if P, then Q, and that's it. Okay, so a truth table that has all my premises. So what are the premises? I'm going to use blue for my premises. So my premises are P, and if P, then Q. And then what is my conclusion? I'm going to use red for my conclusion. The conclusion is right here. Okay, now we complete the truth table. So true, true, false, false, true, false, true, false. Then for P and Q, true and true is true, true and false is false, false and true is false, false and false is also false. If P then Q, if true then true is true, if true then false is false, if false then true is true, and finally if false then false is also true. So now I have a truth table where I have a column for each one of my premises and also a column for my conclusion. Now the next step in the algorithm says, now we need to focus on rows where both my premises in this case are true. So first row, the first premise is true and the second premise is true. So this is a row of interest. Second row, my first premise is true, but my second premise is false. So I'm not interested in this row. Third row, my first premise is false. P is false, so I'm not interested in that either. Also, in this row, one of my premises is false, so I'm not interested in that either. So there is only one row where both my premises, namely P and if P then Q, first column and last column, both of them are true. There's only one row. And what we want is, on the rows where all our premises are true, our conclusion has to be true as well. And you can see that my conclusion is true on the only row where all my premises are true. So what does that mean? It means that P and Q is actually a semantic consequence of these two premises. Now in the next slide, I have a nicer truth table for you, representing the same thing. And here's the way that we write it. If you remember, on the left side, we have our premises. So this is the first premise, second premise. Then we have the double turnstile right here, and then the conclusion on the right-hand side. So the way to read this is P and Q is a semantic consequence of if P then Q and P. Now here's another example. We want to show, or we want to verify, whether P and not Q is a semantic consequence of the propositions if P then Q and not P. So again, the same approach, same algorithm. We need a truth table for all our premises and our conclusion. We have two variables involved, so 4 rows, because there are only 4 possible scenarios for P and Q. So the first column is for P, the second column for Q. Then I need a column for my first premise, if P then Q. This is my first premise, let's call that hypothesis number 1. Then I need another column for my other premise, other hypothesis, let's call that H2. And then I need P and Q as my conclusion, but I need not Q first to be able to construct P and not Q. So P and not Q is my conclusion. Okay, now we fill out the table. I'm going to do that quickly because we have done this several times by now. So you should be able to follow. So if P then Q will be true, false, true, true. Not P will be false, false, true, true. Not Q will be false, true, false, true. And finally, P and not Q. P is the first column, not Q is the fourth column. So we have false, true, false, and false. So now we completed the table. The next step is focusing on the rows where all our premises are true, all our hypotheses are true. So basically where H1 and H2 are both true. First row, H1 is true, but H2 is not, so we are not interested in that. Next row, they're both false, again, not interested. So you see that on the third and fourth row, both my hypotheses are true. Now what I want is, I want my conclusion to be true on every row where both of my hypotheses are true. And you see that in neither one of them, my conclusion is true, which means that this logical argument is not valid. Even if one of them was true but the other one was false, still that's not good enough, because we said the consequence must be true on every row where all the premises are true. Okay, so there you go. Now again, here's a nicer truth table for you. And as you can see, P and Q is not a semantic consequence of those two premises, because on the third row, both premises are true, but the conclusion is not true. And we can say the same thing about the fourth row as well, but finding one such row is enough to show that the argument is invalid. Now here's an example where the propositions are not given to you as P and Q and so on. So you can see that how you can construct a logical argument when we are using natural language. And so we have, if the power pack is not fully charged, then either the amber bulb is lit or the red bulb is lit. So that's one of our hypotheses. The next hypothesis is, if the amber bulb is not lit, then the red bulb is not lit. And finally, our last hypothesis is the amber bulb is not lit. So we have 3 assumptions or hypotheses or premises. And then the thing that we want to see whether or not it follows from those is the power pack is fully charged. So that's my potential conclusion. So we have H1 here, H2, and H3. And this is my conclusion. Now I need to write this down as, P, Q, R, and so on. So let's call this one A because of amber. So A is the name of this proposition here. Let's A be the proposition where it says the amber bulb is lit. So this will be not A. It's not lit. Okay, so A is the amber bulb is lit. So our third hypothesis is not A. And the package is fully charged. Let's call that P. So this means this is not P. If not P, then something. And then the amber bulb is not lit. Again, if not A, then something. Now, then the red bulb is not lit. So following the same kind of argument, let's give the name B, red, let's say R, to the sentence that says the red bulb is lit. So let's call that R, which means that this will be not R. Okay, and finally here we have either the amber bulb is lit or the red bulb. So that's an or of the amber bulb is lit or the red bulb is lit. Okay, so here one more time, A is the proposition that says the amber bulb is lit. So its negation will be not A, the third hypothesis. R is the red bulb is lit. So the second hypothesis is if the amber bulb is not lit, not A, then not R. And finally, the first hypothesis says if the power pack is not fully charged, so let P be the proposition that says the power pack is fully charged, so its negation will be not P, then A or R. And then finally, our conclusion is simply P. So now we are in a similar situation to the previous example. So we have three hypotheses and a conclusion. So we need to draw a truth table and then check every row where all three hypotheses are true and see if our conclusion is true on all those rows. So here is a cleaner version of what I wrote on the previous slide. So P, A, and R are defined to be those three sentences. And then our hypothesis can be expressed in terms of P, A, and R. And finally, our conclusion is simply P. And here's the truth table. Now, again, in particular, we are interested in rows where all three of our hypotheses, H1, H2, and H3, are true. So let me see if I can write them down here. So one of my hypotheses is, if you remember, this was H1. And then we had H2, this guy, and then H3 was this one. So we need to look at a row where all three of these columns are true, or rows, it could be more than one. First row, we are not interested because H3 is false. Second row, not interested. Third row, H2 is false, so that's not interesting to us either. Fourth row, you can see that all of them are true, so that's something to check. Next row, H3 is again false, so that's not relevant to us. Again, H3 is false on the next row, so this is not relevant either. This row here, the row before the last, H1 is true, H3 is true, but H2 is false, so again, that's not interesting to us. And finally, the last row, H1 is false, so that's not interesting either. So there is only one row where all three of our hypotheses are true. And what we want to know is whether or not on that row our conclusion, which is, if you remember, it was P, is true. As you can see, P is true on this row, which means that on every row, there is only one row here, but in general, on every row where all our hypotheses are true, our conclusion is also true, which means that the argument is valid. Or another way, the conclusion actually logically follows from the set of premises.